So thank you very much again for the introduction and inviting me to speak at the GSNI Geothermal Webinar Series. Today, I want to talk to you about finding the heat, and in particular, mapping geothermal gradients using indirect measurements. I'm going to focus on two projects. So this is the De-risking Ireland Geothermal Potential Project, and also the more recent Model Therm project, which is just started. I'd like to first acknowledge all of our funders for the projects. The DIG project is funded by the SEAI and the Geological Survey Ireland, and the Model Therm and Granite projects are funded by the SFI IRC Pathways Programme, as well as the Sustainable Energy Authority. And we have many collaborators that we work with, some quite local, such as UCD, and our colleagues in Cork, as well as the Geological Survey Northern Ireland, and others a bit further away, such as in Potsdam and Madrid. And in particular, I'd like to thank the PIs and co-PIs of both projects who helped write the proposals and get the funding. But onto this. So Michelle gave me a good introduction. I'm 4 years post-PhD. I'm based at DIAS. I was primarily a seismologist initially, so working with seismic data to make tomographic images. I also do some modelling now, so joint geophysical petrological inversions, and I'm also focused on geothermal quite a lot now, although initially I was volcanology. But let's move on to the actual projects. So the first project I want to talk to you about is the De-risking Ireland Geothermal Potential Project, otherwise known as DIG. And the main aim of this was to explore the potential for low enthalpy geothermal energy on the island of Ireland. This was important because we wanted to develop, we want to use geothermal energy in the future. And so I should say that these are all academic projects at the minute, with also assistance from geological surveys, both in Northern Ireland and the Republic. So we broke down this project into several different work packages. We had the full island scale approach to determine a geothermal gradient across Ireland, which I'm going to focus on in more detail. We also had a regional scale approach in the Munster Basin, where we wanted to look at kind of the thermochemical crustal structures and the link between kind of the secondary fracture porosity and kind of the fluids that we had in this location. And then finally, we also had a local focus. This we chose to be the Mallow region. It's an area of known warm springs in Ireland. And so we wanted to further investigate this resource at the reservoir scale in Mallow, and then scale and start to see if it was then applicable in other regions. So my aim was, I was working on the island scale approach and to determine that geothermal gradient in Ireland. And so essentially I was employed to develop subsurface temperature maps. Now, this has been done before by previous studies. So we already have subsurface temperature maps for the island. These have been developed through numerous projects and geothermal projects in the past. So this is not the first project that has been focused on this. Now, the first work was by Goodman et al. In 2004, and they used some borehole measurements and surface heat flow measurements across the island and interpolated between these to make subsurface temperature maps from the surface to about 5 kilometers depth. And this is a slice at 2.5 kilometers depth. But we thought that there might be some anomalies because in the south, we have not very many measurements, and the geothermal, the temperatures here are about 20 degrees Celsius in this model, which are physically not possible when at the surface, the average temperature is about 11 degrees Celsius for the island. So this was developed, redeveloped and looked into in 2019 as part of the GoTherm 3D projects, and IFM kind of also integrated more data into this. And Meta and Villa in 2019 created new temperature models of Ireland. I'm sorry they're not at the same colour palettes nor at the same depth, but this is a 2 kilometre depth slice. And you can see broadly in the centre of Ireland, we have similar temperatures, but we have a significant warming in the south, so we kind of fix some of those kind of too cool temperatures. And also we have warm temperatures in Northern Ireland. Now, you may say, why do we need another temperature map for the island? Well, what is missing from both of these is ground truthing these models and actually checking if they are correct. So it's all well and good saying that you have a temperature anomaly of X, but do we know it's right? So we went out to, first of all, make new temperature maps, but also provide a map of uncertainty for these new temperature maps, which will allow industry partners later down the line to assess, to go investigate regions in more detail before drilling. So these are always a preliminary stepping stone before actually going. So they show you where the heat is likely to be, and also an uncertainty in that to reduce the risk for these companies that go and investigate. And also, we've taken boreholes across the island and where possible, deep boreholes, and ground truthed a model to see how well our model is doing compared to what the actual borehole temperatures say. So that's kind of the background to that. So how do you go about creating a map of subsurface temperature and the geothermal gradient? What information do we need? Well, we need to know where the heat is located in the subsurface. So one area where we have heat is heat from the mantle. And therefore, it's important to know our the boundaries within the Earth. In particular, the lithosphere-asthenosphere boundary is a good constraint on this, because if we have areas of thinner lithosphere, such as at mid-ocean ridges, this warm mantle material is much closer to the surface, and therefore you have a warmer geothermal gradient. However, if we have areas of thicker crust, then these geothermal gradients are much cooler because that heat source is further away. But it's not just about the depth to our LAB. We also need to take into consideration the heat sources in the sediments in the crystalline basement. So we've got radiogenic heat production happening here, and in areas where we have granites, these will also be adding heat to our crust, which will be rising and then have warmer temperatures. So we need to account for this. So in order to make a 3D subsurface temperature using the software that we're using, we require continuous layers for input parameters. We require a mix of parameters. Some of these, as I say, are constraining our boundaries. So we need topography information in the form of elevation. And this is so blocky because this is at the resolution of our velocity information that we have. So our model initially is out at a 0.2 degrees spacing, just to let you know, and it's all done on 1D columns, but we will be improving on that later. We also require phase velocities, so surface waves, because these can help constrain the layers within the crust, as well as MOHO depth and LAB depth, as well as an idea of what that MOHO depth is before we start. We also require surface heat flow, so we want to know how much heat is flowing through our rocks. And we also require information on our thermal property information. So radiogenic heat production, such as this map created by Stephen Daly and Nicola Wilmot-Nola, and also thermal conductivity. And this thermal conductivity map didn't exist before the DIG project, so we needed to create this from existing thermal conductivity points. And I will discuss how that was made later in the presentation. So the main improvement on the meter and per year temperature model was adding in this seismic data, these phase velocities, as these are what constrain our lithospheric boundaries. The reason that this was a good time to do this in Ireland is that we have large lateral coverage of seismic data at this present time. Each of these individual symbols is a seismometer capable of detecting seismic waves, and our method requires cross correlations between pairs of stations to extract the surface waves for both Rayleigh and Love waves, which gives us an idea of if we use both parts of the surface waves, so we have an idea of anisotropy as well. And as you can see, once we use the Great Britain and the UK seismic network, shown by the light blue triangles, we have very good ray coverage across most of Ireland, although there is a slight gap in Northern Ireland, which I'll discuss later. So we can take all of those cross-correlated paths and we can extract phase velocity maps. So we've done this for both Ireland and Britain. and for both the Ireland and UK, and you can see that we have slow and fast velocities by the red and the blue colours. It doesn't matter what these are at these points, don't worry, but you can see that on the whole, Ireland has faster velocities, but at some locations, we have a variation between the Rayleigh and Love, suggesting we need to account for anisotropy. So this is good. So we take all of those inputs and that new seismic data and our thermal property information, and we then do put this into a joint geophysical petrological inversion code. This is called WinTurk. It's developed by Javier Fillea, who's one of our collaborators in 2021. And it essentially is a 1D inversion code. You parameterize a 3-layer crust, so upper, middle, lower crust, and a mantle and a mantle lithosphere and a mantle asthenosphere in the models. And it solves for the heat equations. And from this, we directly invert for temperature. And as other additional projects, we also get shear velocity, lithospheric thickness. We invert for radiogenic heat production, even though it's one of our inputs. And we also get out density and mantle composition parameters. There's a lot of outputs, but the one that we want to focus on mainly is temperature. So what does this look like? So each of these squares on the left is one of the 1D columns that you can see on the right. And essentially, we fit the surface waves and we get a misfit. But what we're really interested in, and I'm just going to fast forward, is the temperature curves and the velocity curves. So remember, each of the colors here on each of these squares corresponds to one of the lines on here. And you can see that for the green, orange, and blue colors, that we have a thicker lithosphere asthenosphere boundary. So we have a thicker lithosphere. And this, if we look on the temperature map, shows that we have a cooler geothermal gradient. So this is what we expected. So this is great. And in addition, the red and the black squares, where we have a thinner lithosphere, we have elevated geotherms. But what's very interesting is that our thinnest lithosphere is actually the black line, but the red line is significantly elevated beyond all the others. So what's going on? Well, what we need to remember is that it's not just the lithospheric thickness that controls the temperature. We also have a heat component from the crust. And it turns out this red square that I've taken here is directly on top of the Donegal granites. So that shows how much you need to take into account your lithology, because it makes a big difference to your model. Now, this is great. We've got a few squares, but we can scale this up. So this is 2 seconds, because this has got stuck. There we go. So this can be scaled up to full temperature maps of the island. As I say, it's a 0.2 degrees spacing, but for visual purposes, I have smoothed these models, as you can see here. I'm showing you depths of 2, 5, 10, and 30 kilometers, but these models go down to 120 kilometers depth. So while it's useful for geothermal, for the shallow, depths for more academic tectonic purposes and working out answering large-scale tectonic questions, we also have information. But I'm going to focus mainly on the geothermal side. So if we look at 2 kilometers depth, you can see that we have warmer temperatures beneath the basalt sequences. And I'm just going to see if I can get a pointer. We have warmer temperatures in Northern Ireland, beneath the basalt sequences, and also where these blue regions are, these are the granite sequences, and you can see that we have warmer temperatures also located here. In contrast, in the south and southwest, we have cooler temperatures, where we also expect to have thicker lithosphere, which gradually, as we go south, as we go towards the northeast, you can see that these gradually become warmer overall. So there's a southwest to northeast trend in the increasing temperatures. I also said, though, it's all well and nice that I created a temperature map, but how confident are we in these results? So what we did to assess this is we looked at a few points. So each of these orange points on this map corresponds to one of these. I'll put the lines on initially, so that's where they're all located, but for clarity, I am going to remove those. So we took points at these, and these points were chosen because they either had the most direct information, so they had the most thermal property information, or they were areas of interest, such as Mallow, where we know we have warm springs. And there's a lot of information on these graphs, But essentially, the black line is our best temperature model, as I show on the left. We then take, at each of these points, we vary the information in the inversion that are most likely to vary our temperature at output temperatures. So these parameters include thermal conductivity, the lithosphere-asthenosphere boundary depth, the MOHO depth, and the radiogenic heat production. We don't include surface heat flow as one of these variables because this is input data that we are trying to fit. The others are inversion variables that we allow to modify apart from thermal conductivity, which is just a fixed value, whatever. We're not trying to fit that. It is just, that is the value. So essentially, we give it ranges for each of these parameters, and then we see how much our temperature varies when we allow all of them to be, when all of these are fixed in the inversion, but we then run all models with all possible values. And these are what these blue lines are. The thick blue line is the mean of these, and the dashed blue lines are the min and maximum possible temperature that you can get, whereas the shaded region is 1 standard deviation. Now, this is great and shows us the maximum variation in our model, and it shows that we have a huge uncertainty. However, this isn't really correct. In the real world, you would never get a rock that has a high radiogenic heat production and then you force above it to have a very low surface heat flow. It's just not going to happen. These parameters trade off with one another. If you have a thinner lithosphere, you're going to have a higher surface heat flow. So we then reran the tests so that we kept only one parameter fixed at a time and allowed the others to vary in the inversion as they would normally be allowed to do. And this is what the green shows. Again, the dark green line is the mean and the dashed lines are the min and maximum, and the shaded region is 1 standard deviation. And you can see that this is a much narrower band. And it's also much less computationally expensive, so it's also more feasible to run it for whole maps of uncertainty. So this is what we did. We ran every single point, we ran all possible models with keeping one parameter fixed and allowing the rest to vary. And then we took the root mean square, we did an RMS average of every single feasible model that was realistic, that had Earth-like properties. And these are what we get out. We have the temperature models on the left, and on the right, we have the output uncertainty models. Now, there's a lot of variation because I kept those fixed, but if we just look at the 2 kilometers, you can see that for the majority of regions, that our uncertainty is less than 3.5 degrees Celsius at 2 kilometers depth. Obviously, as we increase in depth, that uncertainty is going to increase, but that's expected, and shallower it should be slightly less. So this is good. Other things that we can extract from our model we can do a min and max and a mean temperature and how those vary, and they're fairly similar to one another within all of those possible model variations. But more useful is potentially the geothermal gradient that we can extract. So this is an average from 0 to 2 kilometers depth. Because we're just fitting a curve to our data, this geothermal gradient, we don't have individual variations with different lithologies. It's just a 3-layer crust, as I say. It's okay to do an average. A 0 to 2 kilometer average is kind of the same as the whole crustal average. So you can see what the geothermal gradient is, and it ranges from 19 to 38 degrees Celsius per kilometer. And also we can extract the depth to certain isotherms, so like the 30, 60 and 90 degree isotherm, which are important in geothermal industry. We can also, as I say, we inverted for radiogenic heat production. The reason that we did this is that radiogenic heat production is typically on rocks that are found at the surface, but we have layers within our crust, so it's likely to change. And in our model, we only get an average for the full crust. So this is a radiogenic heat production average for the full crust. So we'll be improving this with heat production for different layers in the crust in the future. We also get MOHO and LED maps out. You can see again, as I said, and it matches quite well to our temperatures, that we have thicker crust and thicker lithosphere in the south. And then this thins towards the northeast with the thinnest crust beneath Northern Ireland. So let's have some interpretations here. So for an area of interest, particularly for Northern Ireland, this red outlined area in here is the extent of the basalt sequences, the Antrim lava sequences. And we have elevated temperatures in this region. But what we also have are quite low surface heat flows for the model, which seems a bit peculiar. But we also have, if we look at the thermal conductivity of this flood basalt at the surface, basalt thermal conductivity, so allowing that heat to transport, is very low for a basalt. It's the lowest on the island. So what we think is potentially happening is that the basalt is acting as a thermal blanket, trapping that heat that's rising from the mantle, trapping it beneath this basalt layer, and therefore this would make it a great region for geothermal exploration. And I think new projects are starting to actually investigate drilling, like the Gemini project that's coming up. Another area of interest are the granitic regions. So these are shown by the blue polygons on this model. And you can see in most of the blue highlights, we have elevated temperatures, such as beneath the Galway granites and the Donegal granites. But not all of these areas are as high as each other. The Leinster granite and the Mourne granites are slightly lower temperatures than, say, these two. We also have variable surface heat flow, with some of the highest surface heat flows between the Donegal and Galway ones, and lower surface heat flows between the Mourne and Leinster. And again, the radiogenic heat production is also lower, a variable across between these granite sequences. So what this implies is that maybe that our granites have different compositions, which seems to be the case, particularly if you compare the Leinster granites to some of the Galway granites, but also they're likely to be different sizes and buried to different depths. So it might be that, and also we may be underestimating these resources as well, because each of these inversions is done on a 1D column, so we do not have the lateral heat flow, so possibly underestimating what our temperatures are for these. So I also said that not only would we produce a temperature map and with associated uncertainty, we wanted to know if it actually worked. So we didn't have that many deep boreholes in Ireland. As you know, we've had a lack of oil and gas industry, so there's been a lack of deep boreholes across the region. But we did have 6 deep boreholes at the time that we wanted to use to verify our models. So these are located here by the triangles. And you can see that we've plotted the direct borehole measurement as the solid black line, and our model is the coloured line. And so these are just with that model that we used before. And you can see that in some instances, such as the Grange-Gorman hole, we do a pretty good job of fitting this borehole temperatures, which is very good. For the Ballinleer and the Portmore boreholes, you'll see that they're very close together. They actually have slightly different lithologies, but because they're within 1.2 degree grid cell of our inversion, they actually end up in just one of our inversion points, unfortunately. So we could never fit both of them, given that they have different temperature profiles. However, if we modify the associated thermal properties that we give them to what their rocks are, we can fit each one slightly better. But that's why our model is identical, but we can't fit both of them. I've also plotted, the dashed line is the Goodman model, as you can see here. The dotted line is the Goodman model, and the dashed grey line is the model by Matter and Fiea. So overall, we do broadly a good job, I think. So here's some quick conclusions for DIG. We have produced new subsurface temperature maps of Ireland with uncertainty, and areas of thinner lithosphere have warmer geotherms. We think that crustal depths, the thermal property data is the main temperature control, so those granites have warmer temperatures than expected if it was just lithosphere controls. And what's very interesting is this basalt layer seems to be acting as a thermal blanket. And we've also produced other models. What I've also been working on, though, is to update those maps. We needed a thermal conductivity data. So as part of DIG, we also required more thermal conductivity points to actually input into our model. So initially, we just had point measurements across the island. And these were from a range of sources, so thank you to everybody that has passed on information of these individual points. And given it was our model was quite a smooth model, we basically produced a thermal conductivity map by taking each of these individual points, assigning them to a generic lithology. So we had, I think, several different generic lithologies such as limestone, muddy limestone, sandstones, basalt, and then took the average of all of those points and then related it to the map. And I think GeoSci and GeoServe have a more detailed map for certain units, so you can see that mine's quite a smooth model. But this was good enough initially to make those temperature maps. But we're now working to improve on this because we know that thermal conductivity is not just one value for each layer. So we've been out and taken new measurements. Each of the blue squares over here is a new measurement that we have taken. And these were chosen based on where we had cores, as well as we tried to pick areas with deep wells and undersampled lithologies. We also had to focus on the Mallow region, as this was our focus as part of the DIG project. And we actually took measurements a lot more than we expected to. So I was invited to take optical scanning measurements in Potsdam by the group at GFZ, which was very nice of them, as well as heated transient plane source measurements. And that's shown by the scanner here and the plane source here, as well as divided bar measurements, which I took at UCD with the help of Pablo Rodriguez Salgado, and GeoServe also took many measurements. I'm going to breeze through these a bit, but essentially we got a lot of measurements out. We took 600 measurements using the thermal conductivity scanner, and we had a mix of orientations. So I've taken some averages here and removed some of the orientations. So these are just flat surfaces and both under dry and saturated conditions. And you can see that we have most of the saturated measurements have a higher thermal conductivity, but you can see that all of our rock types have a range. So it's really important that when we do our models, we capture a range, not just a fixed value, which is what we had previously. And also the basalt's interesting. It had an elevated thermal conductivity, what we expected. It had quite a small range though. And this is because it had a quartz crystal in the middle of it, which was affecting our results. So it's probably lower than that. And when we took additional measurements, it was lower. So we also did this for the transient plane source technique. So essentially this is like, it's working out the thermal conductivity of your sample, but it does it at different temperatures. So we put these rocks in an oven and gradually heated them. And what you'd expect is that your thermal conductivity decreases with increasing temperature. So this might have an effect as we go deeper into the crust as well. But what was very interesting is that our basalt kind of keeps a constant thermal conductivity of 1.9. You can see that that quartz crystal was not within this sample. So it is lower thermal conductivity, but it's fairly constant, which was also interesting. We also took measurements on a divided bar. I haven't got all of the results here. I just have my comparisons to the ones that I did at UCD because I'm still processing the ones that were provided by GeoServe. But essentially, we took measurements on a range of rocks, and we got out thermal conductivities here, as well as, and then we did a comparison to the thermal conductivity scanner. And you can see that if we use our corrected values and compare it to the thermal conductivity scanner, most of them are very similar, apart from the granites, which had a lot of variability, which is potentially down to porosity. We're still investigating this. Most of the rocks, though, had 0% porosity or near to that, because we're focusing on secondary fracture porosity. So that's great. We now have a few more points to add to our model. And we're in the process of thinking about how we're going to make a new thermal conductivity map for the island. However, if we use a geological map that's at this kind of scale, potentially we can assign a range of thermal conductivity values for these rock units. However, if we want to do it to the actual geological units, we still don't have measurements on every single, we still don't have thermal conductivity measurements on each of these units. And so we can't really make an accurate thermal conductivity map until we have this. So I'm still thinking about what is the best way to do this in future. So please let me know if you have any ideas. We're also, one of the ways that we did think might be possible is using Raman spectroscopy. Essentially, we took those samples that we took the thermal conductivity measurements on, we then broke them down into their individual mineral components. And if you assign a representative thermal conductivity for each of the minerals, you can then work out what the thermal conductivity of your bulk sample should be, in theory. So this is one method that we're thinking of doing this and comparing it to measured thermal conductivity. And if this works, this might be a way to, if we know the rock compositions, then scale it up across the whole map. So that was for the dig project. But as you could see, particularly from an industry standpoint, where we're going to want to actually drill into these features, a 0.2 degree temperature map is not accurate enough. Although whatever map we produce, it's never going to be accurate enough. You should always go out and do a local geophysical survey and actually go to your area and just verify that it works before you drill. But some of the gaps that we can target and improve in this model already are that our models were very reliant on knowing the rock type. I showed how I tried to compare to those two borehole holes that we gave it the same thermal property data, and obviously we can't fit them because they have different lithologies. But we assumed a simple 3-layer crust, and it's not representative. So we need to fix this and give it a better lithological model initially. Also, our model is a 1D inversion. There's going to be 3D effects. So we're expecting the granite to have lateral heat flow out of the sides, but also, are we capturing all the nuances between this? So we need to think about how we're going to do this as a 3D model, rather than a pseudo 3D stitching together the two 1D columns. So yeah, the thermal conductivity, I've just highlighted what improvements are being done there. And we also have a seismic data hole in Northern Ireland where we don't actually have the crossing ray paths that we need to get a high enough resolution on what the for the surface waves to therefore create a appropriate crustal thickness and LAB thickness model. And this is nice if it works in Ireland, and it's great if it works across the island. But can we go bigger? Can we apply this somewhere else? And particularly in a high enthalpy region, will it work in areas of melt and at a local scale? Most people care about much more local scales, like a city. So can we test this? So this leads me on to the Model Therm project, which is a project looking at modeling the 3D thermal and lithospheric structure of geothermal regions. It's a 4-year project and it started in December 2023. And the main thing with this is trying to fix those gaps. So adding lithological constraints and also increasing independent controls on the results. The main thing is that we're going to integrate lithology. So we need to create a 3D lithology map. We have a new version of the code that allows us to have at least a sediment layer and also to construct several more layers within the crust. It's never going to be at the scale of like the variations within a borehole, but we can improve it somewhat by adding in the sediments. And this will therefore give us a much better model overall. We've also tried to fill that seismic data gap. So I've been working with GSNI, specifically Rob Rain, as well as the Irish National Seismic Network team at DIAS to install 6 new stations across the north of the island with predominant focus here. So this is what our current seismometers that are present in Ireland look like. They've been out for about 1.5 years now. We're hoping to have them out for 2 years, as this will give us enough data because we require teleseismic earthquakes from around the globe to have occurred so that we can then create our models. So we need them out for a sufficient amount of time. And this network is registered on FDSN like normal, so all of this data will be publicly available at the end of the project. So we're filling this. How we do this is that we deploy seismometers that are powered by solar panels. We bury them in a barrel with a concrete base to ground them, and also reduce the noise. And then this connects into a car battery and the control boxes. And we also have to install fences at some of our sites due to cows. We've also been training up people in the building, PhD students. We've had our secretary out in how to actually deploy and service seismic instruments. So it's been also great educationally as well. To check this worked, we co-located it with a permanent seismometer, and you can see that the orange and the blue line is the permanent seismometer and the orange is the temporary, and we basically get an identical signal. So it's working quite nicely. And it's also useful not just for this project, but also for local seismicity. There's not much that happens on our island, but there was an earthquake in Donegal that was located to this pink star here, but we weren't sure if it was a quarry blast or if it was an earthquake. By having the additional seismometers, we managed to geolocate this, and we now know it is definitely an earthquake and also changed the location slightly. I also said that we want to improve on the lithological, the 3D side. So we're going to fit for gravity data. So we're going to take that output temperature models once we've done the improvements with the thermal conductivity and the improvements on the lithological boundaries. And then once we have a new model there, we then put these 1D inversions into a 3D modeling software that will fit for the gravity data. And this will then allow us to have an actual 3D temperature model. The final thing that we're doing is that we also want to see if this works in an area where we know that the geothermal works. So we're going to apply this at the Krafla geothermal power plant. And inversions are going to be run at a local scale. So it's going to be much more important having those boundaries and thermal property data. And it allows us to ground truth this inversion and improve the modeling because we know what the temperatures are there. They're extracting it, so we can ground truth it. There's also, it's a volcanic region. There's melt in the region, so we're going to fit that. So we're going to apply the same methods as are being developed for the Iceland stuff, but apply it to Iceland. And also we're going to develop a machine learning approach to calculate the uncertainty because this will speed things up and also allow us to test significantly more models. And this is going to be done by Bernard Owusu. So essentially, I don't have conclusions as such, but this is what we're going to be doing in the future, and that's how we're going to improve on the initial dig temperature models. Essentially, we have made these models, and we're going to improve these and hopefully make these more useful to people by making these at a much more local scale and a finer resolution. So I'd like to thank everybody that we collaborate with. I'm sure there are many others that I've missed, so sorry to anybody that I've missed, but thank you very much to everybody that helps with these projects. And I'd like to again thank our funders and direct you to our website. So thank you, and if you have any questions, please let me know.